I would like to present you how to calculate the lattice parameters without using any software package. So here I am going to make the use of one of the method, analytical method. So for simplification, I am going to take hexagonal crystal structure for the evaluation of lattice parameters without using any software package. So hexagonal crystal structure. So this hexagonal unit cell, it is defined as A equals to B, nothing but the dimensions of unit cell, both the values A and B are equal, but the length of unit cell C along nothing but unit cell along the Z direction C, so that is not equal to A and B, and simultaneously the angles, crystal angles alpha, beta both are set equal to 90 degrees by the angle gamma equal to 120 degrees. So this is nothing but the definition of unit cell of hexagonal crystal. So if D is the plane spacing, because crystal can be treated as a set of parallel planes, the distance between the parallel planes is nothing but D. So here in case of hexagonal crystal structure, this D value is given by nothing but 1 by D square equal to 4 by 3 into H square plus HK plus K square divided by A square plus L square by C square. So this is the value for D in case of hexagonal crystal structure. So where I am going to make the use of Bragg's law. Okay. So Bragg's law, 2D sin theta equals to n lambda. Okay, the diffracted X-rays should follow this Bragg's law, then only they will be giving the diffraction pattern. So here I am going to take n equal to 1, that means I am going to take a first order spectrum. So 2D sin theta equal to lambda, or if I write the value for D, so lambda divided by 2 sin theta. Okay. So 1 by D value 2 sin theta by lambda. Suppose if I take this one, equation number 1, so substitute this value in equation number 1, nothing but substituting for 1 by D square. Okay, so that is nothing but 4 sin square theta divided by lambda square, which is equals to 4 by 3 H square plus HK plus K square divided by A square plus L square by C square. So from this one I am going to write for sin square theta value. So sin square theta equals to the first term lambda square by 4, okay, 4 by 3 H square plus HK plus K square divided by A square plus the second term lambda square by 4 into L square by C square. So here 4 gets cancelled. Therefore, you can write the value of sin square theta equals to lambda square divided by 3A square into H square plus HK plus K square plus lambda square L square divided by 4C square. Or I am going to represent this equation as sin square theta equals to a constant capital A into H square plus HK plus K square plus a constant capital C into L square. So where the value of capital A constant is lambda square by 3A square and the constant capital C is lambda square by 4C square. So here small a, small c, these are nothing but lattice parameters. So here we did not include the B value because in case of hexagonal crystal structure, both A and B are same. So if capital A is calculated, constant capital A is calculated, we can calculate small a, and if constant capital C is calculated, we can calculate small c. Nothing but lattice parameters can be calculated. Okay. So from this equation, I am going to find the possible values of this form. Okay. So where HKL are matrices. So here I am going to find the possible values for this term. So HK, because it is going to have only two values, H and K. So H square HK plus K square. Okay. So here I am going to take both H and K is 0, 0. Therefore, this value becomes equal to 0. Similarly, if I take 1, 0, nothing but H equal to 1. So H equal to 1, remaining 0 means here I am going to get 1. If I take the combination H equal to 1 and K equal to 1, so H equal to 1, K equal to 1 means this combination value becomes equal to 3. Similarly, if I get the H value as 2 and the K value as 0, so here it is nothing but 2 square, so remaining 0, nothing but 4. If I want to take 2, 1, H equal to 2 and Y equal to nothing but K equal to 1, so H equal to 2, nothing but 4, okay, H equal to 2, 2 into K value 1, so plus 2, here K equal to 1, so 4 plus 2, 1 is nothing but 7, okay. So depending on the different combinations of HK, I will be getting these integer values for this term, okay. So now I am going to calculate capital A value. So if capital A value is once calculated, you can calculate the lattice parameter small a, okay. So here I am going to take, for example, if it is case 1, so case 1 is nothing but calculation of capital A value, okay. So from this equation, suppose if I want to calculate capital A value, so for my convenience, I am going to take, suppose this capital C constant as 0. Therefore, this equation becomes equals to sin square theta equals to capital A into H square plus HK plus K square. Then I am going to write capital A value. So capital A value equals to sin square theta divided by H square plus HK plus K square. Okay. So depending on different combinations of HK value, we have the factor values H square, HK plus K square values. So we have 0. There is no need of taking 0 value. So 1, 3, 4, 7. Therefore here the capital A value. Okay. So depending on HK value, so that is nothing but sin square theta divided by this value. Sometimes if it is 1, so 1. Okay. Then capital A equals to sin square theta divided by this value, so that is nothing but, for example, 3, okay. Similarly, capital A value may be sin square theta divided by this value, so that is nothing but depending on HK value, it may be 4. Similarly, capital A value may be sin square theta divided by 7. Okay. So I am going to draw a table in which I am going to find out the values for capital A. So first column it is going to be sin square theta. Second column it is going to be sin square theta by 3, and third column may be nothing but third column is sin square theta by 4. Similarly, the fourth column is nothing but sin square theta by 7. So I am going to take the help of an Excel sheet in which I am going to assign 4 columns. First column is sin square theta, second column is sin square theta by 3, and third column is sin square theta by 4. The next column is nothing but sin square theta by 7. You can continue the values. So I am going to draw a table that I will show you on the monitor. So from that Excel sheet, you will be getting some numerical values which are repeatedly appearing in these columns. So there is a particular value, particular constant that will be appearing in this column, this column, this column. So you have to search for the value which is repeatedly appearing in these columns. So that value you have to represent as capital A. Okay. If this capital A is known, then you can substitute lambda, which is most commonly 1.54056 angstrom, divided by 3 is a constant. So you can calculate the lattice parameter A. Okay. We will find another lattice parameter, that is small c. So here I am writing k is 2. So k is 2 is evaluation of parameter c. Okay. So for this purpose, from this equation I am going to write for capital C L square equal to capital sine square theta minus of capital A into h square plus hk plus k square. Okay. So depending on the values of h and k, this sum is going to have the values 1, 3, 4, 7. Okay. So h equal to 0, 0, h equal to 0, k equal to 0, h equal to 0, k equal to 1, h equal to 2, k equal to 0. So depending on the different combinations of hk, it is going to take the values 1, 3, 4, 7. Therefore, from this equation you can write CL square equal to sine square theta minus of, suppose this term becomes equal to 1, therefore CL square can be written as sine square theta minus e. Similarly, or you can write this term, if it is equal to 3, so you can write sine square theta minus 3. If this term value becomes equal to 4, therefore same equation, okay, sine CL square can be written as sine square theta minus of 4a. Okay. So here I am going to draw again a table in which one column is going to have sine square theta minus a, second column is going to have sine square theta minus 3a, and the third column is going to have sine square theta minus 4a. So I am going to draw a table, so in which one of the column is going to have sine square theta minus c, the second column is going to have sine square theta minus 3a, similarly sine square theta minus 4a. Okay. So in this table there are some particular values, nothing but the particular value. This particular value is going to be repeatedly appearing in the most of the columns. So there is a particular value that may be appearing in this column, in this column, in this column. So you have to identify the value which is repeatedly appearing in these columns. Okay. So here the value, here the same value you are going to find. Here also you are going to find the same value. So this same value, repeatedly appearing value, is nothing but your CL square, because we have written CL square equal to, okay. So the value which is appearing repeatedly commonly in each column, so that can be represented as CL square. Okay. So you have to identify that one. So if once the value is identified, okay. So here you can see this is nothing but CL square equal to, so this is nothing but the known value. Okay. So known value. So from the Excel table. Okay. So from the table you are going to identify this particular value. Okay. In each column there is a particular value. That value is going to be repeatedly appearing in every column. So that particular column is nothing but, the value is nothing but this one. Okay. So CL square equal to so CL square equal to, so this value you are going to get the Excel sheet, from Excel sheet. So therefore the capital C value can be written as sine square theta minus capital A into h square plus hk plus k square divided by L square. Okay. So to find the value of capital C, the numerator you are going to find from the Excel sheet. But we have to know the value of L. Okay. So the reflections. So from these equations, the reflections are actually H equal to 0, K equal to 0, L. So these are the reflections from which are given by this equation. So here the value of L equal to, it is going to take L equal to 1, L equal to 2, L equal to 3 and so on. Okay. But in case of HCP structure, okay, hexagonal structure, so this 0, 0, 1 is not the reflection which is corresponding to 0, 0, 1 is not allowed. Okay. So this reflection is not going to be allowed in HCP structure. Therefore, this can be treated as, you can treat this one as 0, 0. Okay, instead of calling it as 0, 0, 1 reflection, you can take 0, 0, 2. Okay, so this reflection is nothing but 0, 0, 2 because, okay, the L equal to 1, if I take L equal to 1, the reflection 0, 0, 1 is not allowed, it is forbidden in case of hexagonal structure. So that's why the readings corresponding to 0, 0, 1 can be treated as a 0, 0, 2. Okay, so 0, 0, 2 means here L equal to 2. Okay, so if I take L equal to 2 from this equation, therefore capital C equals to sin square theta minus of capital A H square plus HK plus K square. Okay, so here it is 2 square because I have taken L equal to 2. Okay, that means C equal to sin square theta minus of capital A into H square plus HK plus K square by 4. Okay, so to calculate the capital C value, constant value C, okay, so the numerator you are going to find this numerator from Excel sheet table where you are going to find a column sin square theta minus A, the second column is nothing but sin square theta minus 3A, the third column is nothing but sin square theta minus 4A. So you are going to find 3 columns in which there is a particular value that is going to be repeatedly appearing. That repeatedly appearing value is nothing but your numerator. So substitute that value divided by 4, then that is going to give you the capital C value. Okay, I am going to show you the Excel sheet table in which you can find the value of capital A, the value of capital C. So depending on these capital A, capital C values, you can find the lattice parameters. So here I am going to take an example to explain how to calculate these lattice parameters A and C of a hexagonal structure. So for this purpose, I am going to take the help of the book X-ray Diffraction, a practical approach by C. Subramaniam. So this is the first edition book in which at page number 132, you are going to find a problem. So I am going to solve this problem by using this analytical method. So all this data is shown in Excel sheet, there you can find. So after taking the help of that particular Excel sheet, so the evaluated lattice, the evaluated constants already I have calculated, you can see on Excel sheet. So capital A value 0.113 cap sin square theta minus of capital A H square plus HK plus L square. Okay, so this is around 0.0944. Okay, so this value is repeatedly appearing in different columns: sin square minus A, sin square minus 3A, sin square minus 4A. So there I have taken 3 columns. From these 3 columns, I am going to find this value which is repeatedly appearing. So this is nothing but actually CL square equal. Okay, so here value CL square equals to 0.0944. Okay, therefore capital C equal to 0.0944 divided by L square. So I already told you the L value here 1, 2, 3 and so on. But in case of hexagonal crystal structure, okay, the reflection 001 it is not allowed. Okay, in case of hexagonal structure HCP, okay, this reflection is not allowed. Therefore, I am going to take, okay, 002. Okay, the values which are corresponding to this one, I am going to take 002. So that means here I am going to take L equal to 2. Okay, so here I am going to take L equal to 2. So if I take L equal to 2, this is nothing but 2 square. So 0.944 divided by 2 square value 0.0243. So you can calculate. Okay. So this is the capital C value. So capital C value, okay. Then C equal to lambda square divided by 4C square. So from this equation, the lattice parameter C equals to lambda square divided by 4 capitals. Okay. Or the lattice parameter C equals to lambda divided by 2 into under root of capital C. So this capital C is nothing but this one. So the lattice parameter, if you calculate, this will be nearly in the range of 5 point something. So it is 5 point nothing but 5 angstroms. Okay, you can verify with the given value from the book. So similarly, the lattice parameter A, so lambda square divided by 3A square. Okay, therefore A square equals to lambda square divided by 3A. So A value equal to lambda divided by under root of 3 under root of 3A. Okay. So substitute the values lambda 1.54056 angstrom, root 3 value, capital A value. Then you are going to get the, okay, nearly the range of 2.6 angstrom. Okay, you can cross verify these values, lattice parameter A and lattice parameter C from the given book. So I have taken this problem from the book I have shown you. So this is the procedure to evaluate the lattice parameters. Okay. So from this reference book, I am going to take the XRD characteristic peak positions. Those are 36.31, 38.98 up to 86.54. So I am going to take the peak positions of nearly 10 peaks. So this is the data I am going to take from that particular book. So I am going to insert these values in Excel sheet. So over here I am going to put the corresponding sin theta values will be displayed here. So these are the sin square 2 theta. This is nothing but sin square 2 theta by 3, sin square 2 theta by 4, sin square 2 theta by 7, sin square 2 theta by 9. So these are the columns where you can find a value which is going to be repeatedly appearing in these columns. So that the value will be represented as capital U. Similarly, on the right hand side, you can see we have a sin square 2 theta, sin square theta. So sin square theta minus A, sin square theta minus 3A. So from these three columns, again, you can find a particular value which is going to be repeatedly appearing. That repeated value will be represented as a CL square. Now I'm going to put the values for peak positions. So the first peak position 36.31, next peak, third one, fourth one, fifth, sixth, 7, 8, 9, 10. So if we look for a particular value in these 4 columns, 5 columns. So here you can see 0.11132. So 0.111. So here also we have 0.111. So here also we have 0.111. Okay. So this is the value which is repeatedly appearing. So this one, this one, this one. So I am going to take the average of these 3 values, that will be capital A. So 0.1133, this is the value of capital A. Similarly, to find the CL square value, so here you can see sin square theta minus A. So minus of sin square theta. So this is sin square theta minus of A value. So 0.1133. Okay. So this is the second column. Similarly, I am going to write for third column. I am going to fill the third column. So sine square theta. So this is nothing but sine square theta minus of 3a. So 3 into a value 0.1133. Okay. So these are the three columns. So again we have to search for a particular value which is going to be repeatedly appearing. So here you can see 0.97, I mean 0.097. So here also you can see 0.095 approximately, very close. So similarly you can see here also 0.09. So these are the three values which are repeatedly appearing in these three columns. So the average of these three values will be taken as CL square. So the average value is nearly 0.0944. So this is the value for CL square. Okay. So in the beginning we have taken CL square equal to sine square theta, actually that is sine square theta minus of capital A into h square plus hk plus k square. So depending on the value, depending on the combination of h and k, here this factor may be 1349 something, 1347. So the first column you can see sine square theta minus a. So this is sine square theta minus a. The second column is sine square theta minus 3a. If I take third column, nothing but next column, that will be equal to sine square theta minus of 4a. Okay. So these are the three columns in which there is a particular value that is going to be repeatedly appearing. That particular value is nearly 0.944. So the value of sine square theta minus capital A into h square plus hk plus k square will be 0.0944. So from this I am going to calculate capital C value. So numerator is nothing but it is a common value. Okay. So that will be 0.0944 divided by L square. So here L can take the value L equal to 1, L equal to 2, L equal to 3 and so on. But in case of hexagonal crystal structure, the 001, okay. So here this is nothing but 001 reflection. So this reflection is not possible. So this reflection is not possible. Therefore, this particular refraction 001 can be taken as 002. Nothing but you have to take L equal to 2 in this particular reflection. So here I am going to take L equal to 2. So if I take L equal to 2, so capital C equal to 0.0944 divided by 2 square, nothing but 4. Okay. So then this capital C, the capital C value now becomes equals to 0.0944 by 4. So which is equals to nothing but this capital C value. This capital C value now becomes equals to 0.0236. Okay. So this is the value capital C and this is capital A. So if we know capital A value, capital C value, then easily we can calculate the lattice parameter small a and small c.